Alright guys, welcome to the channel. We're going to be solving question 16 from the second chapter of the Johnston textbook, Mechanics of Materials. And this one we have a 250 millimeter aluminum tube, which we know that the Young modulus is 70 gigapascal. And we have the information about the outer diameter 36 and the inner diameter is 28 millimeter, and the tube can be closed at both ends by means of a single threaded screw-on covers of 1.5 millimeter pitch. And let me just explain a little bit about this part. So what it means in here by single threaded, it means that we have a screw that has a one continuous helical thread winding around its shaft. And by the screw-on covers, it means that the covers attach by twisting them onto the threaded part. And we also have 1.5 millimeter pitch, and that refers to the distance between two consecutive threads, which is 1.5 millimeter, and it means that the cover moves 1.5 millimeter along the screw axis with each full turn. But what the question is asking, with one cover screwed on tight, and also we have a solid brass rod, which again we have the elastic modulus. We know the diameter is 25 millimeter, you can see in the figure 2. And since the rod is slightly longer than the tube, it's observed that the cover must be forced against the rod by rotating 1/4 of a turn. So if we do 1/4 of a turn, it can be tightly closed. So as I mentioned, we have a 1.5 millimeter pitch. So if the cover moves 1.5 millimeter along the screw axis on each full turn, here we can close the screwed covers by a 1/4 turn. So what's gonna happen in here is that the rod is gonna get compressed and the tube will be in tension. So what we need at the end is that the deformation of the tube has to be equal the deformation of or the movement that we have from the quarter turn that we have. We can show it with delta Q, or I just show it with delta Q, which is that displacement from the one corner turn plus the deformation of the rod. So it's easy enough to find the deformation of that 1/4 turn because we know it's 1/4 of, and as I said, each turn is 1.5 millimeters. So since we have a quarter of that, we have 1.5 divided by 4. So we have 1.5 divided by 4, which is going to be 0.375 millimeter. And for finding the formation, I explained the formula in the previous video that where we get this, we basically have force times the length, which is the initial length that we have, over elastic modulus and the area that we have. So we need to find this for each of them. And before jumping to that, let's just find the area and the length, the area of each, because after that, uh, we already have the elastic modulus and the length and everything. So we're gonna end up with just 1p, which we have. So let's just find the area of the rod first. So the area that we are dealing with for the rod is this circle. Since we have the diameter, we have pi over 4 times d, which is 25 squared, and we're gonna multiply this by 10 to the minus 6 in order to get it in meters. So we're gonna have pi times 25 squared divided by 4. So it's gonna give us 490 times 87, 0.87 times 10 to the minus 6 meters squared. Let's find the area of the tube. And for finding the area of tube, basically we have the area of the outer diameter minus the area of the inner diameter. That way we can find the area of this ring in here. So pi over 4, we can basically factor pi over 4. So the outer diameter squared, which is 36, minus inner diameter 28 squared, and that's going to give us 36 squared minus 28 squared times pi divided by 4. So that would be 402.12. Again, we'll have 10 to the minus 6. I forgot to put it in here to get it in meter squared. So now that we have this, we can find the deformation for each of them. Let's start with the deformation of the rod. So P, we don't know what's the value of the P, but we should be able to find it. And the length is 250 millimeter. We're going to divide it by 1,000 to get it in meter, divided by E. And we know for the rod, we have 105 gigapascal. So 105 times 10 to the 6. So 105 gigapascal, 10 to the 9. And the area we already found for rod, 490.87 times 10 to the minus 6. So if we calculate this, we're going to have our force in Newton. So let's see what we get. So we're going to have 0.25 divided by 105 times 490.87 times 1000. We're just going to cancel out 10 to the minus 6 and 9. So this is going to be 4.85 times 10 to the minus 9. And I forgot one thing. So since the rod is in compression, we're going to put a negative sign in here. So we're going to get a minus P times 4.85 times 10 to the minus 9. And that's going to be Newton. We're going to have the same scenario for the tube. No negative sign for tube since it's in tension. So I think for the E we had 70 instead of 105. So 70 times 10 to the 9. And the area is 402.12. 402.12 times 10 to the minus 6. And this is going to give us 0.25 divided by 70 times 402.12 times 1000. And that's going to be P times 88 times 10 to the minus 9 Newton. So if we get back what we had in here, we should be able to find the P from, we know what we have for the deformation of the tube, which is P times 8.88 times 10 to the minus 9 is equal to what we found for our twist. So if we want to report this in meter, it's going to be 3.75 times 10 to the minus 4. Or if we want to keep everything 10 to the minus 6, it will be 375 times 10 to the minus 6. So 375 times 10 to the minus 6 plus what we found for rod, which was minus P times 4.85 times 10 to the minus 9. So if you bring this one to the right and factor P, basically we have 375 times 10 to the minus 6 over 8.88 times 10 to the minus 9 plus 4.85 times 10 to the minus 5. So this is going to be basically 375 divided by 8.88 plus 4.85. And if you factor 10 to the minus 5 in the denominator and bring it up, we can cancel these. So we have to multiply this by 1,000. So our forcing here would be 27.31 times 10 to the 3 Newton. So now we found the force P, which was the hardest part of this question. After this, in the A part, we just have to find the average normal stress in the tube and the deformation for each of these. So for deformation, we just have to put what we found for P in each of these. So pretty easy. And for the tensile stress, let's go with the rod first. We're gonna have, since the rod is in compression, we'll have the force over the area of the rod. The force is 27.31 times 10 to the 3 Newton, and the area of the rod, let's get back from here. for area of the rod, 49.87 for 90.87 times 10 to the minus 6 meter squared. That's going to give us the force in Pascal. So we're going to divide that by 490.87. So that would be minus 0.0556 times 10 to the 9. So that's going to be also, we can write it down as 55 minus 55.6 megapascal. So that's for the rod. If we want to find the tube, since the tube in tension, there is no negative sign. A, the area of the tube, same force, 27.31 times 10 to the 3 Newton over the area, which was, we have in here 402.12. And let's see what we're getting here. 27.31 divided by 402.12. That's going to be 67.89 times 10 to the 6 Pascal, or 67.89 megapascal. So that was the answer for the A part. And as I said, for the B part, we just have to multiply our force P in order to find the values of the deformation for each of these. I'm just going to show it in here. So will be minus what we found for P, 27.31 times 4.85 times 10 to the minus 9. And we had the same thing in here. This will be plus 31 times 3.88. Let's calculate this. So minus 27.31 times 4.85. We missed the 10 to the 3 for the force. So this will be 10 to the minus 6. Same here. And if we just divide this by 1000, we're going to get it in millimeter, because what we have in here is based on meter. So we're going to get minus 0.132 millimeter. That was for the rod. So that's what's for a rod. And for a tube, we're going to get 27.31 times 8.88 divided by 1000. In order to get it in millimeters, 0.243 millimeter, and that's the deformation for the tube. So yeah, that was a long one. Hope everything was clear. Let me know if you have any questions, and you guys take care. I'll see you in the next video. Have a good one.